look at today is more of what's, we're going to kind of bring everything together, because as I hope somewhat obvious, a bit of what we've been looking at is a little artificial. We have to do that to get started. So we started with axial loading and looked at the normal stresses associated with that, and then some of the shear stresses. We looked at torsion, which was entirely shear, if you remember. And then we put in later some bending, and that used most of the very type of loading that we happen to look at in statics, and is some of the most common of the structural type loadings that we'll look at. And then we looked just on Monday at the transverse shear loading that we can see. Now we're going to put all of these together in some combination and see what they all have to do with each other. Before that, we have to take a little bit of a step. This is considered a combined loading. I'm not exactly sure why, because it really only is a strict and particular type of loading, and that's the type of stresses seen in thin-walled pressure vessels. This is a huge part of the mechanical engineering industry. There's the government regulations that need to be observed in terms of thin-walled pressure vessels, all built on the very type of thing we're going to look at now. It's just immense. You can imagine what the kind of failure if a high-pressure vessel fails, and the sudden release of that pressure can be catastrophic, even in ways you might not anticipate. Back in Boston in the early 1900s, I forget exactly when, there was a molasses tank that was holding, was full of molasses. The pressure, due to the hydrostatic pressure of that molasses, ruptured the tank and caused a flood. And as embarrassing as this is as a way to die, 100 people or so were killed in a molasses flood. And I believe, if I remember, it was in January as well. So they couldn't outrun cold molasses, which is, I imagine you get up to the pearly gates and you got some splaining to do, because that's just a terrible way to go. There are better ways. So we're going to look at thin wall pressure vessels. So we'll take kind of a look at a spherical cap just to get the picture going. So there's some elemental piece in this. And we're assuming that these are all high pressure vessels on the inside. So this is like a spherical tank, and what that high pressure on the inside causes is tension in all directions in the material that makes up the pressure vessel itself. And so just trying to give it the appearance of a curved surface like that. We're going to see then the normal stress throughout. No resistance to bending in this, and all forces are tangential in nature. So be a little more specific now, and we'll start with a look at a cylindrical pressure vessel. So we've got it in cutaway. Of course, it's got some kind of cap on the end. High pressure vessels don't do well if you just put a flat piece over the end, because as I just mentioned, there's no resistance to bending of these very thin materials, and that end cap would be almost entirely in bending. So it's typical that a more rounded piece is put on that, and that's exactly what you see with scuba tanks and the like. So we've got this pressure vessel with an associated coordinate system. First, though, let's make sure we understand what we mean by thin wall. We have R, the inside radius of the tank, and then there's some wall thickness T. And it's the ratio of those two that we use as our definition, as arbitrary as it might be. We define a thin-walled pressure vessel as one where the radius to the thickness is greater than about 10. So if we had a 10-inch inside radius tank, any wall thickness less than 1 is going to be considered a thin wall pressure vessel. All right, then as we had before on the little spherical picture, we've got a little elemental piece there, and that's going to see two types of normal stresses on it. There's going to be a hoop stress that we call sigma 1. I don't know why we can't call it sigma h, but not one of the books I have looks at it as that. So sigma 1 is a hoop stress. Hoop, obviously, because it goes around the vessel, as the type of metal hoops you'd see if we were looking at oak barrels and the like. They have exactly that type of thing, and we'd be looking at the stress. In fact, we have a couple problems in the book looking at pressurized oak barrels with metal hoops running around them. And then there's a longitudinal stress called sigma 2. Down the length of the vessel itself in its main dimension R. All right, we need to take this apart and see what we can make of these stresses themselves in regards to the load they're carrying, which is the internal pressure. This internal pressure is considered a gauge pressure. You may have heard the term before, gauge, but it's precisely the type of reading if you happen to have a pressure gauge and you attach it to some kind of nozzle that could read the pressure in the tank. It's merely the pressure over atmospheric. That's all your pressure gauge reads when you take the pressure in your tires. It's how much pressure there is in the tire in addition to the atmospheric pressure. What that allows us to do is we only need to look at the forces caused by the internal pressure. We don't need to balance that against the outside, the atmospheric pressure also pushing on the pressure vessel in towards the center. We can just ignore that because we subtract it off of both of them, so we only have the pressure above atmospheric to worry about. If we consider the atmospheric pressure and use the absolute pressure on the inside of the tank, they just subtract anyway because they're exerting equal and opposite forces on either side of the wall. So we're only going to look at the gauge pressure. We'll use, in a fit of creativity, the symbol P, and now we can look at the type of stresses that we've got there. So we'll start with a little segment of the vessel down the X direction. So we'll take a little piece of it that runs like this. So what we've done is we've got a little piece of the tank, some length delta X, and I've cut it right in half and exposed that tank. The type of thing we've done before where we're just imagining a cut through the tank to expose the internal forces in the material itself. So when we do that, we've got this internal pressure that's pushing out on the tank. Now, you have all, bless you, you have all taken Physics 2, I believe. Is that right? You looked at David, have you?
I did take Physics 2, but I'm not sure if we covered this at
so. What I'm looking at is the hydrostatic pressure, the pressure of a fluid on a solid surface. And in this case, we have a curved surface. Now, it might seem problematic at first because the pressure is a force that can act normally to a surface only. There's no transverse ability of pressure to exert any forces. So the pressure is going to be acting around the surface like that, normal to the surface in every place. And if you remember from hydrostatics in Physics 2, if you actually covered it, there was a small section, you can pull out your physics book, it'll show it, the forces on submerged curved surfaces. It may seem somewhat problematic because you're going to need to integrate over the entire curved surface on the inside. What it turns out, though, to end up in result is very, very simple. You only need to look at the projected surface and the forces normal to that. This happens because every upward component of force has an equal and opposite downward component, and they all cancel. So any of the, let's see, this would be our y direction. Any y direction component to the forces cancel each other, and the result is that you only need to look at the equivalent pressure acting on a projected area to get the total force acting on that curved surface, which makes it a lot easier for us as we balance the forces, because we're balancing the forces really in the z direction because of the exposed surface we've got there. So we've got this projected area, which is nothing more than the rectangle there, with these, my perspective on my drawing is off a little bit. We've got pressure, the gauge pressure acting on that, and that's all we need to consider, and that'll give us the equivalent pressure of having done it all the way around the surface, normal to the surface. We'll get the same equivalence. So we've got those forces trying to push that cylindrical, that hemicylinder, the semi-cylinder towards the minus z direction, and then of course the internal forces in the material, which is what we're trying to find, are acting in the opposite direction to balance those, because we have static equilibrium in all of our situations that we work with. Remember, this is in the hoop direction that I'm looking at now. So we can balance the forces on this piece here and see what they equal, and that'll allow us to find the stress. So the first part I guess we can do is we have this pressure acting on that that area. That area is twice the radius times delta x. So that's 2r delta x. That's the pink pressure force exerted by the fluid. Due to the fluid pressure. Whether this is compressed air or simply liquid storage, liquids being so much heavier than gases, they tend to exert a lot of pressure in their own right. So that's the pink pressure. That's got to be balanced by the stresses in the material itself, which is delta. It's the stress acting on the area of the wall that's exposed, which is delta x times t, but there's one top and bottom, so it would be 2t delta x. And that's the due to internal forces in the wall itself. All right, so everybody comfortable with the picture for the most part? We're balancing the fluid pressure forces trying to push this in the minus E direction, and the internal forces in the wall itself as it tries to hang on to the other half of the tank that we've taken out of the drawing. And so this simplifies quite quickly. The delta x's cancel, the 2's cancel, and we get then the hoop stress, sigma 1 is equal to P R over T. Units work out okay? Always check our units as we go through algebra.
Yes, I believe so.
Yeah. Remember, the units on stress are the very same units as pressure. In fact, we often use Pascal, which is a standard unit of pressure. So it works out just fine. For the units of pressure in Pascal. We wouldn't capitalize the A, that stands for area. We don't capitalize units. There we go. And so that's the hoop stress. It's as simple as that. We need to know what the gauge pressure inside the tank is, and then actually multiply it by that ratio that we use to define the thin wall limit itself. So it's a pretty straightforward calculation there to find the hoop stress. All right, to find the longitudinal stress, we need to make the cut in the other direction. So it's very much like the picture we've got there, so I'll just redraw it here so it's a little bit bigger. kind of exaggerate the wall thickness so that we can see all the parts of it. And now we've got the same type of thing on this projected area here. We have the fluid pressure acting. So that's going to, the force acting over that area is the force in the, I guess what would be minus x direction. And then we have this internal wall force as the wall tries to hold itself together, acting all the way around on this exposed bit of wall that we've cut open in the imaginary way we've been doing this all along. And so again, we need the two forces to sum to zero, otherwise we won't have static equilibrium. So we have the fluid pressure acting on that projected area, which is just the inside radius, inside circular area, pi r squared. So again, that's the force due to the fluid. And that must be balanced by the internal stresses in the material itself to withstand those forces, as this pressure is trying to rip the tank apart, the tank's trying to hang on as best it can. So due to the thin wall approximation, all we need to do to estimate this area is, we'll just call it 2 pi r times t. It's not quite that. It's, you know, I guess have to do 2 pi r outside minus r inside and then times t. Or no, r average I guess would be a better one. But this is close enough with the thin wall approximation. And so that's the internal wall forces. And we can then solve for the longitudinal stress. Pi cancels, 1r cancels, and we get then P over 2 T R. Is that right?
PR?
No, P times R over 2T. Notice that that's half the hoop stress. So it's the circular direction, the hoop direction, that's going to be the greater of the dangers of the two. So that's our longitudinal stress. Okay. Fairly straightforward. These aren't severely difficult calculations, so we'll do a couple problems just to make sure we can work. Oh no, what we have to also do is, this is for a cylindrical tank, but most of these tanks will have a circular end cap on them. So we have to do our analysis for that. So we'll now look at a spherical tank. There are some tanks that are completely spherical. They're more difficult to make, but they do use less material, as you remember from probably Calc 2 or 3, the maximum volume for the minimum material is for a spherical shape, which is why God makes water drops round, in case you were wondering. So we'll now look at a spherical tank.
I'm guessing it's also probably one reason why Soviet space capsules are often spherical.
Yeah, well, that's a pressurized, thin-walled pressurized vessel.
Except the atmospheric pressure P is equal, close to zero.
Yeah, so
I'd like to look at a problem like that.
the gauge pressure and the internal absolute pressure are essentially equal. In this case, since it's spherical, there is no preferred direction. It's going to be symmetric in all directions, so we only need to figure out a single stress. Hoop, there is no hoop direction, there is no longitudinal direction, so there's only this one single stress we need to figure out. But we'll call it sigma 1, since that is the worst case over in the cylindrical tank, so we make sure that we're looking at the right one. So if we make a cut through the middle to expose this, we get the same kind of picture we had before. Now we have a hemisphere cut open with fluid pressure like that, and internal wall stresses like that. We get essentially the very same picture we just had, and we get the very same solution, PR over 2T. Okay, so now we can look at a quick problem. Throwing some numbers here. So imagine a long cylindrical tank with spherical end caps. Something like that. Maybe a little longer than we might see, but you see propane tanks outside of summer camps all over the Adirondacks. So this very same type of thing. All right. Tank is 8 feet long. The cylindrical part has a wall thickness of 3/8 inch and made of steel. It's 30 inches in diameter, and the end caps themselves are 5/16 inch steel. Or as we'd say, 5/teens. We wouldn't say that, it's too embarrassing to say. We'll give it a gauge pressure of 180 psi G. The G means gauge, psi gauge pressure. You might also see, you'll see this when you take thermodynamics, that there'll also be pressure readings in psi-A, which is pounds per square inch absolute. That then includes the effect of atmospheric pressure, which we don't need to do because the atmospheric pressure in is subtracted off the part of the atmospheric pressure that's also in there. We just use the difference between the two. Okay, so we've got two pieces to look at. We've got the end cap to look at and see what the stresses are in there, make sure that it won't exceed the steel limits. And that's the part we just came up with. There's no preferred direction to the symmetry of the sphere. So you can just put the pieces in and double check to make sure your unit's all right. So that's up to you. Take a second to do that. And then in the body of the tank as well, we have two types of stresses to calculate. The signal on the hoop stress and the longitudinal stress. And then we can compare those against stress limits in steel. These happen to be well under that, so we don't have to bother with that. But just check the numbers, check your units. This 30-inch is the outside diameter. So technically you need the inside radius, and it's not 15. You have it there, 14.84. Well, that's not quite what I had. 14.69. Oh, I'm sorry, you're looking at the, yeah, I'm still not getting 14.84. And there's going to be, pressure vessels tend to have a very large factor of safety on them anyway, so if we're off by a few little bits, it's going to hopefully get swallowed by the rather large factor of safety. Get your units. Okay, I think most people are getting the pieces there. Pressure 180 psi. What do you have for R? You had 14.84. What do you have? We'll get different things for R. You have 13 point something. We're all over the map. No, that's the outside diameter.
516.
Oh, minus, okay. Yeah. Yeah, for the end cap, it's 15 minus 5/16. What's that equal?
Like special. Like, why can I get this? Oh,
were you doing, Tommy? You were off in a completely different, 13 something. $14.688. Is that right, John, finally?
6875.
Yeah. We don't need too many significant figures on those type of things. And then the thickness itself. Five sixteenths. And then the same kind of thing, same pressure, slightly different R and T on the tank body calculations. Now that is not PSIG because these are not fluid pressures, these are stresses that we're calculating here. There's no such thing as a gauge stress, it's not that I know of. Bill, you got that number? Alright, so we already know what all the units are in that. Pressure is the same, this time R is 14.625. And the wall thickness is 3/8, 375. And we already know all the units are okay. And then we only have to cut that in half to get the other one. And then half of that's 35. Agreed? Joey, okay? No?
Got the first one. I just followed mine.
What, you got this? Or that one?
No, I got that one.
But not this one? Not yet, or not agree with it?
Not yet.
Okay. But others agree with it? You're okay with the 70, 20? All right. Finish that one. Do another real quick one. The ultimate stress.
The yield, is that the same thing?
No. Well, it depends. If you remember when we looked at our stress strain diagrams, the yield stress is the end of the linear part. The ultimate stress is the highest it goes up to. What's up? Yeah, the yield stress is what you're worried about in structural materials, because when the load is released, you want the stress and the strain to be released too. Ultimate stress would be for other materials. For example, this problem we're looking at is that of a basketball, and you never use a basketball uninflated. Well, sometimes you have to because you can't find the needle that you lost when your dad told you to put it away where you were supposed to and you didn't. So you can't find the needle, even though every household has 12 of them. Nobody knows where one of them is. Not that I'm speaking from practice on my own. The ultimate stress for rubber is about 2,000 psi. We don't need to worry about the yield stress because we're not going to pump up a basketball, then unpump it and use it. We're going to pump it up, and you want to make sure that it'll take as much pressure as you can put into it and not burst. So typical outside diameter for a basketball about 9.5 inches. Wall thickness of the rubber about 1/8 of an inch, and typical gauge pressure is about 9 psi. So determine about how much margin of safety there is to that ultimate pressure for the rubber. And will you let your kids play with a basketball when it might be on the verge of exploding, taking out his eye, suing the school district for millions of dollars, and you drive nice cars for the rest of your life?
They won't let kids play with us like
That's pretty much
dodgeball
parent.
anymore.
Oh, well, that's more of an issue for
Those nice hard
self-esteem.
red one.
Yeah.
So,
Those
oh,
are
you
self-esteem
need
issues.
the
Yeah.
saucing over mediocrity.
Well, it's in dodgeball, when you get hit, you have to go line up on the side so everybody knows you're out, and then you're not playing. Everybody plays in America. Come on, you've got kids. You guys are kids. You grew up in that world. You guys are all in the depression that you can do anything you want. The adults in the room, me, know better. All right, so figure out if we've got a pretty good margin on this.
Should be probably a good experiment. Just see how many basketballs you can blow up at one point. Recorded. It's a good Saturday
Look,
afternoon. What
That's,
are you looking at?
see, yeah, I think the Mex Club should do some Mythbuster type things, you know, do tests like that, see what'll happen. Joey will sign up.
You will get a case of beer.
Yeah, just what I want to do with 18-year-old students, thanks a lot.
What's the ULD?
All right, now you should be getting an internal pressure, or internal stress. You're looking for the stresses in the wall of the basketball. And I notice everybody's getting, oh yeah, okay, I was reading wrong. So we're all getting about the same number. What, a factor of safety of 12, give or take a little bit? Yeah, you should be getting all the units work out okay. We're at a 9 PSIG. The radius, I think, comes out to be 4.625. And the inside wall thickness, that was given 4.125. And so we get a stress in the wall material itself, in the rubber of the basketball, of well under the expected breaking stress. So it's not common to find basketballs that will rupture on the playground. Okay, I think we'll do one more real quick just to give a different illustration of the type of thing that will happen. So let's look at a storage tank. Now in this case, the entire tank is not under pressure because it's only the hydrostatic pressure of the fluid in the tank itself. So you're not going to need a spherical end cap on the top of this because that's not significantly under pressure. It's the bottom down here that's going to see the greater pressure since the pressure varies with depth in the tank. So we'll give it an 8-meter outside diameter, a 16-meter height, But the, we don't need that 16 meter, we'll just use 15.5 meters of fluid, that's what matters. It's the height of the fluid. Unless it is a closed tank and the space above it is pressurized, which could happen if they're worrying about, you know, you want the tank to empty quicker, you pressurize the tank to force it out faster. So a wall thickness of 16 millimeters at the bottom. Determine at the bottom what the hoop stress is then. And we know the longitudinal stress is half that. So the one thing you'll need is the density of water, which is 1,000 kilograms per cubic meter. So we'll see if you remember how to determine the pressure at the bottom of a column, of the bottom of a liquid column. And we're assuming the top is open, so it's open to atmospheric, so this would be the gauge pressure at the bottom. Let's see who remembers how to figure out the pressure at the bottom of the fluid column. Did you guys do some hydrostatics and fluids in physics too?
Like I said, we didn't do that at RIT.
You didn't? Yeah, that may
Maybe I'm wondering.
depending upon the sequence, some schools put that in physics 3 and put other stuff in physics 2.
I don't think we probably would have done physics 3, because physics 3 at RIT was a lot like
Oh,
physics 3 here, we did electrical stuff.
Is there
Yeah.
1 atmosphere for 10 meters?
So,
I don't know, something like that. Yeah, I guess it would be. Pressure at depth is a function of the density, actually the specific weight, and the height of the fluid column. The top. You can do without the conversion if you just use rho GH, where rho is the density of the fluid, G is the gravitational field strength, so that together is the specific weight, where density is actually specific mass, and then H is the height of the fluid column, which is the 15.5. So if you do that, then you're not in units of atmospheric pressure. Atmospheric pressure is about 14.7 psi, if I remember.
What is that in pascals or something times? I think it's about 50,000.
Yeah, I don't know, I don't remember. I tried my best not to memorize conversion factors, because then when you get them wrong, you don't know it. So you look them up each time, and then you know they're right. Plus my memory sucks. If my memory sucks, I'll be a medical doctor. I'll be driving a Porsche with a blonde by my side, not you guys. Man, that'd be life.
doesn't
It's
sound
not
like
equal.
much punishment for having poor memory.
That's not. Wait till you're 57. A Porsche and a blonde sounds pretty nice. Good thing my wife doesn't watch these videos. She gave up on those long ago. Figure out the pressure, rho GH,
At the bottom?
at the bottom, because the pressure is much greater at the bottom. In fact, the gauge pressure right at the top is 0, because it's atmospheric pressure at the top. There's no fluid weighing it down. And then once you find that pressure, you can just figure out figure out the radius thickness is given. Other than that, you do have some units to worry about, because we've got some meters and some millimeters in there, but that's pretty minor. So that'll give us newtons per cubic meter, whatever that means. I guess that, yeah, that's the specific weight. And then times the 15.5 meters. So that'll give us newtons per square meter or Pascal. Kilopascals.
Do we need to subtract the atmospheric pressure?
No, that is the gauge pressure. Because you're only worrying about the fluid column weight itself above that spot. So that, and there is no designation like kPa(g), at least none that I've ever seen, where it would be kilopascals gauge.
I just saw one on Maple syrup Twitter.
Yeah?
Is that weird?
It had kilopascals?
Yeah.
Wow.
It's a reverse
That wasn't Vermont.
osmosis machine.
Actually, it could have been Vermont. They're pretty progressive over there.
Greenwood.
Or Greenwich, a little pocket of liberalism. All right, so we've got all the numbers there. I hope you do, at least. Then we've got the 152 times 10 to the 3 pascals, Newton per square meter, so the units will all work out. The radius, 3.984, right? Remember, that's the inside radius. That's the outside radius that's given there, so have to subtract the 16 millimeters off of that. And then the wall thickness was just 16 millimeters. So you get what, 37.9 megapascals? And then you can check that against the yield stress. Since this is something that needs to work both stressed and unstressed, because the tank's empty and full at different times, then you probably want to design for the yield stress rather than the ultimate stress like we would have with the basketball. Okay, take our next step into, remember what we're looking at is combined loading. So far, we've got normal or axial stresses that we've looked at. That we came up with very early, and it's the same type of things we were looking at here. Let me not use a P there, because that looks too much like the pressure. It's a force over some unit area. We also just added bending stresses, and that was, if you remember, due to whatever the bending moment was. They were a maximum at the farthest away piece of the material with respect to the neutral axis over the moment of inertia of the cross-section. We also had in here shear stresses. First was caused by torsion. Which was the applied torque times the radius of the piece over the polar moment of inertia. And then we just had the transverse shear stresses that we just added That's the VQ over IT. So we've, over the term, put together those 4 types of stresses. 2 normal stresses, 2 shear stresses. Now we're going to look at the possibility of loading such that these things will be combined. For example, we could have a beam that was loaded in this fashion. Simply supported, in fact, as simply as it could possibly be, just 2 main supports, and then some kind of load in here. What we typically look at is some kind of load like this. So we'll put 3.6 kilonewtons there, and that'll be it. This will be 375 millimeters. We'll put 1125 millimeters over there. Nothing new there. But remember what we started the term with was axial loading, so let's go ahead and throw that in too. We have not before looked at these 2 things in combination. Turns out it's very easy to handle. What we get here is, well, the axial loading that we started with, which is just simply this 25 kilonewtons. This one happens to be in tension. This is the stuff we were doing the first week when we added on this kind of thing. I'll give you a cross-sectional shape and area of the beam of 50 by 75 millimeters. So simple rectangular shape. And so we figured out back in the first week that the normal stress was the load being carried by a particular cross-sectional area. And we've got all this for this axial load. 25 kilonewtons being held by 55 by 75 square millimeter area. And that comes out to be 6.75 kilopascals in tension. And we have to pay very close attention to whether we're talking about tensile or compressive forces now. Because in addition to that, we also have this bending that we figured out just a few weeks ago. Just before break, we were looking at the bending. And you can figure it out for yourself, but this leaves a maximum moment of, well, we can figure it out, I guess. Yeah, the maximum moment comes just before here. And you could prove that to yourselves with a quick shear moment diagram if you want. Comes out to be, well, it's the reaction here, which is 2.7 is the reaction on that side. So it's that times the moment arm by the time it gets all the way over there. which is the full 375. Remember, the maximum moment occurs right at where that load is. I don't happen to have that number. Because what we really need then is the stress that that maximum moment causes. What is that moment, John?
10, 12, 25.
And 12.5, that would be kilonewton meters. All right, that's what we need. That's causing the bending. C, well, due to the rectangular cross section, we know that C is half of the 75 millimeter height, which is 37.5 millimeters, 0.375 meters. And what's I for rectangular cross section, do you remember? 1/12 BH cubed. Now that's just the bending stress, remember? That comes out to be 21.6 megapascals. Because here's the deal with what's going on. We've got this beam due to under the axial loading. Let me label this the bending. We've got the axial loading that puts a stress profile that looks something like this. It's in tension all across the beam, and it's, well, we're looking at the average, so it's uniform, and that's the 6.75 kilopascals. That's just the axial effect alone. We have to add to it this bending effect that we've got. Which looks like this. We know that it's linearly distributed about the neutral axis. In this case, the neutral axis is right down the center. And because of the type of bending we've got compression in the top of the beam and tension in the bottom. What we figured out here, remember, was the maximum stress. Now those two effects are happening at the same time on this beam, so we need to add those together to get the real effect of the stress on the beam due to the combined loading. So that's going to look something like this. On the top of the beam, we have tension stresses combining with compressing stresses, so they're going to cancel each other to some measure. We have 6.75 stress and tension on the top half of the beam, and subtracting from a maximum of 21.6 on the bottom of the beam, so it's going to look something like, well, I don't have that number. What's 6.75 minus 21.6? 15 something. 6.75 in tension and a maximum of 21.6 in compression on the top. What?
-14.
So this
25.
is, we have at the top of the beam, we have a compression of 14 point who?
8.5.
We'll call it 14.9 kilopascals. So we're essentially subtracting, well, adding these two, one constant, one linearly distributed, so we get a linear distribution of something like this. At the bottom of the beam, we're adding the 6.75 in tension with the 21.6 in tension at the bottom of the beam. So that should be 28.3.
Is it? I think it's, one of them's in,
I think the arrow's in the wrong direction.
What?
I think we think the arrow's in the wrong direction.
no, one of them's in APA.
Well,
21.
depends on how you draw this. This I show going in as compression would. It's going from outside the solid
21.
inside, so that's compression.
It's in MPa, megapascal.
Oh, megapascals.
No, but the other one's in KK, so it's, the difference is like nothing.
Which one's which?
21.6 is megapascal.
Isn't this as well?
No, that's kilo.
I have, this is actually megapascals. And I happen to write kilopascals.
Okay.
This is megapascals? Yeah, so we're still adding them. Let's fix that. Kilopascals there. And I hadn't written down the other one. So this is megapascals. All right, and so that's megapascals there as well. All right, but we have a lot less of it in a lot less compression and a lot more of it in a lot more tension. And notice that the neutral axis has shifted too because of this combined load now. And so now our maximum normal stress is this 28.3 at the bottom, which neither one of them approached independently. But it's as simple as that, as simple as adding these stresses together. All right. Nothing more than a superposition of the stresses that we're calculating. So I'll set up a problem, we'll get started, and we'll finish it very quickly on Monday. So imagine we have a bracket fastened to a wall here. Bolted through. And there's some kind of, I don't know what it would be called, some kind of thing over there, to which we attach a 250-pound load. And this slope there is 3 by 4. So some of the other dimensions. That dimension there is 1 1/4. That's from the bottom up to the top part of the bracket, because we want to look at the stresses in the bracket at 2 places. we want to look at it at one place right here and one place right below that. So one place in the middle we'll call A, and one place right at the bottom that we'll call B. So it's an effect, we're looking at one place up here in the middle to see what the stress is, and we're also looking at one place at the bottom. So up to that middle piece, it's 1 1/4. It's 2 inches from the load over to those places. And the cross-section of the piece looks like this. It's 1/2 inch high and 3/4 of an inch deep. So we're looking at the 1/2 inch cross section there. So what we're going to get is some axial force due to the horizontal component of this that's trying to pull this bracket in an X direction, if you will. Then we also have some bending component due to both of those components. Both the horizontal component is trying to bend it one way, the vertical component is trying to bend it the other way. Whichever one of those is dominant tells us which direction the bending is there, but we need to add that stress to the axial stress that we're also feeling. So let me give you some of the things just to help you through this. What we call the section properties, which are those pieces of the geometry that we will need for the calculation of each of these. We'll need the cross-sectional area, of course. That's 0.375 inches squared. We also need the moment of inertia, the 1/12 BH cubed, because it's a nice rectangular cross-section. That's 0.07825. Inches to the 4th. 0.07825, yep. And then there's also shear going on for both of these. So we're going to need Q, and we're going to need it for both points. Now, if you look at the cross-section, the neutral axis, of course, is right through the center. And so the Q for point A, which is right in the middle, is this entire area above there. And you calculate this and double check it. Remember, it's just y bar A is 0.234,375. 0.234,375. We'll carry a lot of significant figures through till the end, just because some of these numbers are very, very small, but you need some of the detail until the end. Now, QB is a little bit different. Remember, B is at the very bottom of the piece. So what is Q for that? Remember, this Q is based upon the area beyond the point of interest away from the neutral axis. And there is no area beyond the neutral axis. We are at the extreme point, so that is 0 for point B, because it is on the outermost bit of material. Don't think that we always do the area above the neutral axis, because that implies that this has something to do with gravity itself, which it doesn't. It has to do with where the forces are and where the points of interest are that we're concerned with. So we'll have axial stress combined with the bending stress, and then we'll also have shear due to the transverse component of the shear on either point. So we'll finish that up on Monday then, since we're out of time.